Welcome to my class on statics. I've been teaching statics at an engineering college for over 20 years, taught statics several times, and I've been starting to make video recordings mostly for my students who miss class. But if you found it through some other source, that's great. You're still welcome as well. Hopefully, this will help fill in any gaps in your statics understanding. So, since this is the first day of class, I want to go over a quick background of what is statics and why are we here together. So, a definition of statics is we are focused on rigid body mechanics of equilibrium. Well, that's a lot of big words, so let's break them all down. What rigid body means is we assume that there is no deformation of anything. So every object we look at, even though it's going to have forces applied to it, it's not going to stretch out or get longer. Now, in the real world, things do change shape because of the loads applied to them. But in many engineering structures, when we're dealing with materials like concrete, steel, and aluminum, often those deflections are small enough that it's okay to neglect them for some parts of the analysis. So we're focusing on no deformation. You could also say there's no deflection in this class. And this is just a simplifying assumption. Later on, in a class on mechanics of materials, you will need to get rid of that simplifying assumption and start actually calculating deformation and deflections due to load. What is mechanics? Let's do the mechanics part next. Mechanics is the response of objects to forces. You have been doing mechanics and physics for probably at least a whole semester if you've made it into this class now. And in physics, what we're doing is we're applying a force to an object. Maybe the force is gravity. You're throwing a tennis ball up in the air, and the forces that act on it, air resistance and gravity, determine how far it flies, how fast it flies, where it lands, and all of that. Mechanics is just all about how does an object behave due to the forces applied to it. In this class, we are going to be dealing with specifically equilibrium. What that means is we're going to assume that there is no acceleration. If you want to deal with acceleration, you will need to come back for another class on dynamics. For this class, we're dealing with the simplifying assumption, and we're assuming nothing deforms, nothing deflects. There will be forces on objects, and we want to find out what those forces do to those objects under the constraint that we are going to analyze conditions where there is no acceleration. Governing everything we do are Newton's three laws. I'll bet you know what they are already. One of them we often sum up by just saying inertia. This is that one that says that an object in motion stays in motion, and an object at rest stays at rest unless acted upon by a force, right? Newton's laws are all about forces. Second one, you probably saw it as something like F equals ma. I'm going to put lines underneath everything in this class that is a vector. Forces are vectors. Acceleration is also a vector. Now, Newton says that if I apply a force, actually, Newton also says the summation of all the forces. If I sum up all of the forces acting on an object, the net force is going to cause my object to accelerate, and how much it accelerates is going to depend on how much mass it has. That's a great equation. We are not going to use it in that form in this class. Do you remember what I said about acceleration? No acceleration this semester. So instead, in our class, this simplifies to summation of all the forces has got to be zero. We're going to call that our equilibrium equation. And we often have to say there are several of them because we can write this out separately for the forces in the x direction, the y direction, the z direction. There's another equation here that we often forget about when we're talking about Newton, but it's that the sum of all the torques is equal to something called mass moment of inertia. We'll just use a J for it, times angular acceleration. Okay, you use this with things like rotating discs, and you want to figure out if you apply a certain torque, how much will it accelerate? Again, in our class, it's going to simplify to the summation of the torques are zero, and we're actually all often going to use a different symbol for torque, but we'll get there in a couple of weeks. These equations are going to be central to solving problems in here, and for this class, the right-hand side will always be zero. Got to come back and take dynamics if you want to actually solve for accelerations and angular accelerations. This third one is the one about actions and reactions. So something like for every action, there is an equal and opposite reaction. This one we use all the time in this class. Think about it this way. If I have a box and it is sitting on a table, I want to look at the forces that the box and the table are applying to each other. They will always be equal and opposite. So if I go to draw a free body diagram of just the box, well, you're going to have the weight of the box on it. And then what is that table doing? is pushing up on the box with what we call a normal force on the box. And if that's all that's happening, maybe the normal force is equal to the weight of the box when we're done. But then if I go to draw the free body diagram of the table, here's where Newton comes in. The table, we're going to have the weight of the table, but now it was in contact with the box. So if the table was pushing up on the box to hold the box in position so it doesn't fall down, the box is pushing back down on the table with an absolutely equal and opposite force and box. And finally, I guess this was sitting on the ground. So I removed the ground was probably pushing up with normal force from the ground. But where Newton's law comes in this picture is this normal force on the box comes as an equal and opposite pair. If two objects are pushing on each other, the forces have to be equal and opposite. So when we go to draw free body diagrams, we're going to make sure that they are, if one is up, the other one is down. And if we call it n box, we're going to call that one n box as well. All right, we have dealt with Newton. Now we need to deal with units. Units are absolutely critical for success in statics. And could I say every other engineering class you're ever going to take? And here's why. If I say something weighs 10, it weighs 10 pounds, that is very much not equal to 10 newtons, and it is definitely not equal to 10 kilonewtons, and it is not even equal to 10 kilograms, which isn't even a force unit. You can't ever give me an answer without units attached to it, or it is wrong. And if your problem is in pounds and you suddenly have a unit in newtons, that's wrong. And if you're looking for a force and you give me units that are kilograms, when kilogram is not a unit of force, that's also wrong. When it comes to conversions between units, we're going to do a few of them this semester. I think you'll do more in later classes, but here's how I like to do conversions. Let's say I had an area of 1 square meter and I needed to convert it into square millimeters. Well, I like to multiply by 1 because when I multiply by 1, I know I haven't changed anything. So let's be very clever with how we multiply by 1. There are 1,000 millimeters in 1 meter. So now I've multiplied by 1, haven't changed anything, and now I can cancel that meter with the squared part of the meters. But if I leave it like that, I've got 1,000 millimeters. Well, I wanted millimeters squared, so I need to do this again. Another 1,000 millimeters per 1 meter. So I'm multiplying by 1 again. I'm not changing anything. And now that other meter cancels the other meter, and I'll be left with 1 million millimeters squared, especially when you're converting with units that are not as simple as just meters to millimeters or newtons to kilonewtons. If it's more complicated, if you've got something squared or cubed or anything more complicated, I strongly recommend multiplying by a clever form of 1 so that you end up doing the right number of conversions. So you end up with 1 million square millimeters and not 1,000 square millimeters. The other main unit mistake that students make in here all the time is mass versus weight. The thing to keep in mind is that we've got the world of SI units over here in which mass is given in kilograms, but force or weight is given in newtons. And how are these going to be related? Well, 1 newton is 1 kilogram meter per second squared. So if I have something has a mass of 500 kilograms, that is not the weight of the object. To get the weight of the object, I need to do m times g. Well, that would be 500 kilograms times g is 9.81 meters per second squared. That comes out to be 4,905 newtons. That is the weight. So here's the mass, 500 kilograms. There's the weight, not 500 kilograms, 4,905 newtons or 4.91 kilonewtons. That's for SI units. The reason that I think that this confuses us is that in our book, we're going to be doing a mixture of SI metric units and English units. In English units, we don't deal with mass in this class. The only thing you're going to be given if it's English units is you will directly be given the weight of the object. So in English units, we are simply given pounds, and that is our weight or force unit. Not using pound mass in here. Every time you see pound, it means pound force. Metric, you're going to be given mass in kilograms. You need to convert it by multiplying by g, 9.81 meters per second squared, and that will give you your force in newtons. And then we're going to be summing forces, right? Newton's law said we're going to be summing forces. It didn't say we're summing masses. We're summing forces. So we do have to convert kilograms to force in newtons. All right, let's talk for just a minute about significant figures In my class, and I would say in the majority of engineering classes you will ever take, our goal is to round our final answers to 3 significant figures. So that's for our final answers. But I do want you to keep all decimal places for intermediate calculations. Let me show you what examples of 3 sig figs are. With the acceleration due to gravity, we're going to use G is 9.81 meters per second squared. That is 3 sig figs. 10 is not 3 sig figs. 9.8 isn't 3 sig figs. We're going to use 9.81. If we needed G in English units, we're going to use 32.2 feet per second squared. 2 examples of 3 sig figs. Let me give you an example that is not 3 sig figs. Force equals 99.999 newtons. It's too many decimals. I know a lot of students sometimes mistake sig figs with number of decimal places. Look, this one had 2, this one had 1, but they are 1, 2, 3, 1, 2, 3. Count the number of digits. This would be 1, 2, 3, 4, 5 sig figs. Too many, too much precision. So let's round that and make it 3 sig figs. Well, there are 2 ways to get your answer. This rounds, because it's got so many 9s, this could round to just 100 newtons. And if the answer does round to 100 newtons, I'm okay with you giving me the answer as 100 newtons. If in your 3rd digit, right, we want to round right here, and the problem is that it's got a 9 after it that brings the 9, it rounds up to 100. So this is not as precise. What would be better would be to call this 1.00 times 10 to the second newtons. Scientific notation makes it crystal clear that we've kept 1, 2, 3 sig figs. So if I'm grading something and the answer actually rounds to 100 with your 3 sig figs, I'm okay with both of these as being correct, but this second one is more precise if you want to be super precise. Now, what I don't want you doing is taking a number like forces equal 129 newtons. Do not round that to 100 newtons. That would be 1 sig fig, right? And this is why I'm saying that 100 newtons is a little bit ambiguous, which is why this is preferred from a precision standpoint. But I've already worked out the problems you're doing for your homework and test. I know this number rounds to 100. I am not going to take mark off for calling 99.9 100. But if you call 129 100, now we've run into problems because you've gotten rid of all of your precision and you've taken that down to just 1 significant figure. Best would be using scientific notation, making it super clear that you're rounding to 3 sig figs. In your intermediate calculations, I definitely want you keeping more decimal places though, because if you start rounding everything to 3 sig figs early on and then you start doing calculations, you want to keep at least 4 or 5 digits of precision for your intermediate calculations. So just round at the end. Why do we do this? If I were to go and try to measure a force that's around 100 newtons in my lab, I do not have a load cell that is capable of measuring a force this size down to the, 1,000th of a newton. And so in engineering, it's not that more decimals is more accurate. These extra digits here don't mean anything. If you thought about trying to measure a length with a tape measure, if you're measuring a very long length, you're not going to be able to measure it to microns of accuracy. You can measure small things with microns of accuracy, but you can't measure big things with microns of accuracy. So 3 sig figs is a really nice sweet spot in engineering. We're going to spend all of the next several classes talking about vectors, but I want to just give you guys a really brief intro to vectors for a second. So you will remember vectors have magnitude and direction. Idea here is that if I have a force that is 10 pounds, it's not just 10 pounds in any old direction, it's 10 pounds in a specific direction. And so then let me draw on here an x-axis, a y-axis. Let's say I have another force, 3 pounds in that direction. And I want to add these 2 force vectors. Well, I would need to know a little bit more information. I need to know what orientation is this one at. But when we have vectors that have a magnitude and direction, it makes a really big difference which way the 10 pounds and the 3 pounds points to figure out how they add up. And the answer when I sum these is not going to be 13 pounds because I need to account for the direction that they act in. The way we're going to be summing vectors this semester is going to be by breaking them up into their Cartesian components and then summing them and then finding the resultant. Let's try theta of 20 degrees. Call it F2. We'll call the blue one F1. F1 is going to be, the magnitude is 10 pounds. Now for the x direction, I would need to use, you can think about it as there's a triangle here. If you guys remember SOHCAHTOA, the side adjacent to the angle is the cosine side of the angle. So I can just take the 10 pounds times cosine of 20 degrees. That'll give me my x component, and I'm going to use a little I with a hat over it for the x component. And then plus, I'll have 10 pounds times the other one. Sine of 20 degrees gives me my j component. How do I figure out sine and cosine? Again, I break this up into a triangle, and I know that the side adjacent over the hypotenuse is the cosine of the angle. And then I multiply by the hypotenuse again to get that side of the triangle. And the side opposite, I'm going to use the sine, and then times the 10 pound gives me this length right here. I've got F1 broken up into components. Let's break F2 up into components. Well, it'll be 0 in the I direction, plus all 3 pounds are in the j direction. Now let's sum them. The resultant force, we're going to use the word resultant to mean the sum. This is the resultant. Well, that's going to be, we're going to add up the i's. So 10 pounds cosine 20 plus 0. There's my I component. And then we'll have 10 pounds sine of 20 plus 3 pounds. There's my j component. Let's get some numbers. This first one is 9.3969 I. It's got units of pounds. The second one becomes 6.4202 J. You'll notice I kept a lot of decimal places there because this is an intermediate step. And that all has units of pounds. So that means that my force would go over 9.3969 and up 6.42. So there is my resultant force. If this side is, this is 9.3969 is how far it goes in the x direction. In the y direction, we go 6.4202. I'm not quite done. It's really nice at this point to find what is the magnitude of FR. If I want to find the magnitude, it works really well is to think of this as a triangle. We just figured out this length of the sides. Let me actually write them along the side. That side is that long. This side is that long. We can use Pythagorean theorem to get the hypotenuse, which is the magnitude. It's going to be the square root of 9.3969 squared plus 6.4202 squared. The number comes out to be 11.381. That would be pounds, but for the final answer, I want to round this to 3 sig figs. So my final answer would be 11.4 pounds, nicely rounded to 3 sig figs. The other thing we often want to find out is what is that angle? What is the orientation? And the easy way to get that angle is to recognize that the tangent of theta is the opposite, 6.4202 over the adjacent side, 9.3969. Inverse tangent that, and you get the orientation. And that comes out to be 34.34. We'll round it to 3 sig figs, 34.3 degrees. And I think those numbers make sense. My original force, I was going up and to the right 10 pounds, but it was 20 degrees. Then I go up a little more. So my final answer should be a little longer than 10, and the angle should be a little bigger than 20. That's it for today. When we come back next time, we're going to do a lot more vectors, and we're going to get into 3-dimensional vectors.